Welcome to Unknown Genesis 4K. One ocean, one question. Which species truly reigns supreme? The Pacific stretches across more than 63 million square miles of open water. It reaches from the Arctic to the Antarctic, from the shores of Asia to the coastlines of the Americas. It holds more water than all the world's land masses combined could fill. It contains some of the deepest trenches on Earth and some of the most shallow, sun-soaked reefs. It is ancient, complex, and alive in ways that challenge every assumption we bring to it. And it has rulers. Not one, but many, each dominant in its own domain, each supreme in its own way. But only one can truly reign above all others. That is the question we are here to answer. And to answer it honestly, we cannot simply crown the largest animal or the fastest predator. True supremacy in an ocean, this size and this complex, means something deeper. It means control. It means influence. It means the power to shape everything around you, to be so essential to the system that without you, the entire structure begins to unravel. By that measure, the contest is tighter than it looks, and the answer is more surprising than most people expect. We begin where power is most visible, at the top. When people think of ocean predators, they think of teeth. They think of speed and force and the raw capacity to kill. By that instinct, the great white shark seems like an obvious candidate for the crown. It is one of the most feared animals in the ocean, built over 400 million years of evolution into a hunting machine that has outlasted the dinosaurs, survived every mass extinction in Earth's history, and persisted through ice ages, continental shifts, and radical changes in ocean chemistry. The great white shark is one of the most ancient designs still operating in the Pacific today. Its body is a study in engineering, streamlined from nose to tail, with skin covered in tiny tooth-like scales called dermal denticles that reduce drag and channel water flow around the body with almost frictionless efficiency. Its teeth grow in rows, with new ones rotating forward to replace lost ones throughout its lifetime. Its jaw exerts one of the strongest bite forces of any animal ever recorded. Its lateral line system can detect vibrations in the water at distances that would seem impossible. Its electroreceptors, called the ampulla of Lorenzini, can sense the faint electrical fields produced by the heartbeat of a prey animal buried in sand. A great white can hold body temperatures higher than the surrounding water, a rare ability in fish that gives it a metabolic advantage in cold Pacific waters. It can accelerate from a slow cruise to a full-speed burst in under a second. It breaches completely out of the water when striking from below, a strategy designed to deliver a catastrophic first impact that incapacitates prey before the animal can fight back. Everything about it says apex predator. Everything about it says king. And yet, watch what happens when a great white shark encounters an orca pod. The great white retreats. Every time. Without exception. The shark that nothing else challenges becomes hesitant, evasive, and then absent. In documented interactions around the Farallon Islands off California and near Gansby in South Africa, great white sharks have abandoned feeding areas entirely after orca pods arrived, in some cases staying away for weeks. Scientists have tracked individual great whites relocating hundreds of miles in response to the presence of orcas in waters where they had previously spent years. The greatest shark on Earth defers to the orca. That tells us something important about this contest. The orca, which science classifies as the largest member of the dolphin family, is an animal of extraordinary contradiction. It looks like a predator shaped for power, and it is, but its real dominance comes not from size or speed or bite force. It comes from intelligence, from cooperation, from the ability to solve problems in real time, to adapt hunting strategies to new prey in new environments, and to pass those strategies down through generations the way human cultures pass down knowledge. An orca pod is not a collection of individuals operating by instinct. It is a coordinated unit operating by plan. Individuals take specific roles in a hunt, with some driving prey towards shallows, while others block escape routes, and still others waiting in precise positions to deliver the killing strike at the moment of maximum chaos and minimum resistance. These roles are not random. They are rehearsed, refined, and remembered. Young orcas spend years watching and practicing before they are trusted with critical positions in a hunt. Different orca populations in the Pacific have developed entirely distinct cultures. Resident orcas off the Pacific Northwest coast specialize almost exclusively in salmon, with individual pods showing preferences for specific salmon species and specific hunting techniques suited to the rivers and coastal waters of their home range. Transient orcas in the same region hunt marine mammals, including sea lions, harbor seals, and gray whale calves, using completely different strategies. Offshore orcas venture into open water and target sharks, including great whites. Each population has its own dialect, its own vocabulary of clicks and calls that identifies members to each other and is incomprehensible to orcas raised in different dialects. This cultural diversity means that orcas are not one type of predator. They are many types of predator wearing the same body. They can occupy multiple ecological niches simultaneously across the Pacific, hunting different prey in different ways, in different environments. No other large marine predator comes close to this breadth of dominance. And yet the orca is not the answer to our question. Not yet. Consider what the orca depends on. Its intelligence is extraordinary, but intelligence requires fuel. And the fuel for every orca, every pod, every culture of hunters in the Pacific comes from below. Remove the fish, remove the marine mammals, remove the krill and the zooplankton that sustain everything the orca eats, and the most sophisticated predator in the ocean starves. The orca controls the top of the food web, but it does not control the food web itself. It is, in the end, a passenger on a system built and sustained by forces far smaller and far more fundamental than any whale. Before we reach that fundamental layer, there are other contenders to consider. The blue whale makes its claim not through aggression, but through scale. It is the largest animal that has ever existed on this planet. Not just the largest living animal today, but the largest animal in the entire known history of life on Earth. Its heart is the size of a small car. Its arteries are wide enough for a human child to crawl through. Its calls, which fall mostly below the range of human hearing, travel thousands of miles through the ocean, making it the loudest animal on Earth by some measures. Nothing that has ever lived on land or in the sea has exceeded its size. When you encounter a blue whale in the Pacific, you are looking at the pinnacle of biological scale. The blue whale's strategy for dominance is so counterintuitive that it almost seems like a mistake. The largest animal on Earth eats some of the smallest. Krill, tiny shrimp-like crustaceans that are barely a few centimeters long, are the almost exclusive diet of the blue whale. A blue whale can consume up to 4 tons of krill in a single day, lunging through krill swarms with its mouth open and its pleated throat pouch, expanding to engulf thousands of gallons of water at once, then pushing the water out through its baleen plates while the krill remain trapped inside. This strategy works because of scale. The blue whale doesn't need to be faster than any individual prey item. It only needs to find the swarms, which can stretch for miles in the upwelling zones and frontal systems of the Pacific. And when it finds them, a single lunge delivers more energy than most predators extract from a week of hunting. The blue whale has resolved the energy equation of the oceans most efficiently as any animal ever has. It converts the ocean's most abundant organism into body mass at a rate that has never been matched. And in feeding, the blue whale does something that nothing else its size does. It shapes the chemistry of the ocean around it. When blue whales feed at depth and then rise to the surface to breathe and defecate, they transport nutrients from deep, cold water into the sunlit surface layer. This process, called the whale pump, fertilizes the phytoplankton blooms that form the base of the entire Pacific food web. A blue whale is not just consuming the ocean's productivity. It is generating it. Its mere presence and movement through the water column drives the chemical cycles that make abundance possible for every other species in the system. Fewer blue whales means less nutrient cycling. Less nutrient cycling means smaller phytoplankton blooms. Smaller blooms mean less zooplankton, less krill, less food for the fish and seabirds and other whales that depend on those resources. The blue whale's disappearance from a region of the Pacific doesn't just remove one species. It downgrades the productivity of the entire system. That is influence. That is power. That is something close to supremacy. But is it the top? Let us now turn to a contender that operates in plain sight and is so familiar that we rarely think of it as a ruler of anything. Dolphins are among the most widely distributed marine mammals in the Pacific. From spinner dolphins in the warm tropics to Pacific white-sided dolphins in the cold northern waters, the dolphin family covers the ocean in a way that no single large whale can match. They inhabit coastal waters and open ocean. They dive to significant depths and feed at the surface. They are generalists in a system that rewards specialization, and their generalism is a form of dominance that outlasts the specialists in times of change. A dolphin pod is one of the most sophisticated social units in the ocean. Individuals recognize each other by unique signature whistles, the equivalent of names. They maintain long-term alliances with specific companions that last years or even decades. They cooperate in hunting in ways that rival the orca's coordination, though typically at smaller scales and with less dramatic results. They play, a behavior that in most animals signals cognitive surplus, the ability to do more with a brain than bare survival requires. Spinner dolphins in the tropical Pacific have developed a hunting strategy that turns the boundary between light and dark water into a weapon. They dive into the deep scattering layer, the dense community of fish, squid, and crustaceans that descends during the day and rises toward the surface at night. Working together, they disorient and concentrate their prey in a coordinated pincer that leaves almost no escape route. When the hunt is over, they rise to the surface and leap in the spinning jumps that gave them their name, an exuberant behavior that may serve as a social signal, a way of communicating the outcome of the hunt and coordinating the pod's next movement. Dolphins also serve as regulators. By feeding heavily on mid-level fish and cephalopods, they keep the population of those species from growing so large that they exhaust the zooplankton and small fish below them, remove the dolphins, and the middle tiers of the food chain can swell into instability. The stabilizing effect of dolphin predation is quieter and less dramatic than the orca's hunts, but it operates across a far wider range of the ocean and touches more species simultaneously. Now we must step back from the predators entirely and look at a different kind of power. The great white shark rules through fear. The orca rules through intelligence. The blue whale rules through scale and chemistry. The dolphin rules through ubiquity and social complexity. But there is a category of ruler in the Pacific that operates without any of these advantages, that has no brain, no behavior, no movement of its own, and yet exercises more control over the fate of the Pacific than any vertebrate animal in the water. Phytoplankton. These are single-celled organisms, some of them barely a few micrometers in diameter. They cannot swim against a current. They cannot hunt. They cannot defend themselves. They drift wherever the ocean takes them, dividing and multiplying when conditions allow, and dying when conditions change. They have no nervous system, no awareness, no agency. They are among the most passive organisms on Earth, in any conventional sense of the word. And they produce approximately half of all the oxygen in Earth's atmosphere. Every second breath you take comes from phytoplankton in the ocean. The entire terrestrial biosphere, every forest, every grassland, every animal that has ever walked on land, exists within an oxygen budget that phytoplankton help to maintain. The Pacific alone, which contains the largest volume of ocean water on Earth, is responsible for a staggering share of this global oxygen production. The blue whales, the orcas, the sharks, the dolphins, the humans watching this film, all of them breathe because phytoplankton exist. But oxygen production is only the beginning of phytoplankton's influence. They are the foundation of the food web. Every krill that a blue whale eats grew by eating zooplankton, and every zooplankton that grew in the Pacific did so by eating phytoplankton. Every salmon that runs upstream to spawn in a Pacific Northwest river accumulated its energy from a food chain that began with phytoplankton. Every orca that coordinates a hunt across miles of open ocean does so on energy that began as sunlight absorbed by a cell too small to see without a microscope. Remove phytoplankton from the Pacific, and within weeks, the zooplankton populations collapse. Within months, the fish populations collapse. Within a year, the marine mammals and seabirds begin to starve. The entire food web, from the smallest copepod to the largest blue whale, is built on top of the productivity that phytoplankton generate every day in the sunlit surface layer of the ocean. The great white shark and the orca are impressive rulers of their specific niches. Phytoplankton are the foundation on which every niche in the Pacific is built. They are not alone at the base of the system. Zooplankton, the small animals that feed on phytoplankton and are in turn consumed by fish and larger invertebrates, are the transmission layer between the invisible foundation and the visible ocean. Copepods, krill, amphipods, pteropods, and larval stages of countless larger animals form this layer, and their numbers are almost incomprehensible. A single cubic meter of Pacific surface water can contain thousands of individual zooplankton. Across the Pacific surface, their combined biomass exceeds that of all the fish, mammals, and birds in the ocean combined. Krill deserve special attention in this contest for supremacy because krill are not simply a food source. They are a currency. The Pacific krill economy is the mechanism through which solar energy becomes whale. A krill swarm can stretch for hundreds of square miles and descend to depths of several hundred meters during the day, creating a vertical migration that moves carbon from the surface to the deep every single night. This daily migration is one of the largest movements of living matter on Earth, and it is driven entirely by the behavior of animals that are individually the size of a human fingernail. Blue whales target krill. Humpback whales target krill. Fin whales, minke whales, and sei whales all target krill. Salmon eat krill. Herring eat krill. Mackerel eat krill. Penguins eat krill. Albatrosses eat krill. The Pacific food web converges on krill the way a river system converges on a delta, and the health of every species that depends on krill is directly linked to the abundance and distribution of this one small crustacean. If krill are the currency, then the Pacific economy rises or falls based on whether the currency supply remains stable. So, who controls the krill? The krill population is governed by the abundance of phytoplankton on the one hand and by the pressure of predation on the other. And the predation on krill is so intense from so many directions simultaneously that krill only survive and thrive through numbers. There are so many of them, reproducing so rapidly, that even the most intense predation cannot consume more than they can replace. This is the math of the base of the food chain. Abundance at the bottom sustains scarcity at the top. Now let us think about a ruler who operates at the middle of the system rather than at the top or the bottom. The Pacific salmon is not the largest fish in the ocean, not the fastest, not the most powerful, but it performs a biological function that no other species replicates, and that function connects ecosystems that seem to have nothing to do with each other. A Pacific salmon is born in a freshwater stream high in the mountains, sometimes hundreds of miles from the coast. It spends its early weeks learning the chemical fingerprint of that stream imprinting it into memory with such precision that years later it will use that memory to navigate back to the exact same gravel bed where it was born. It then migrates to the ocean, where its body undergoes a complete physiological transformation. Its kidneys rewire themselves to handle salt water. Its skin changes color and reflectivity. Its muscles build out from months of feeding on the ocean's bounty. In the open Pacific, salmon contribute to the midwater food web as both predator and prey. They consume krill, herring, and smaller fish, accumulating energy in their bodies that represents the output of the entire Pacific food chain below them. And they are hunted in turn by orcas, great white sharks, dolphins, sea lions, and every seabird large enough to take them at the surface. Their presence in the open ocean touches the lives of dozens of species across thousands of miles of water. Then they return. Driven by hormones and magnetic navigation and chemical memory, they swim back to their birth stream to spawn. And when they arrive and die after reproducing, something remarkable happens. Their bodies, saturated with marine nutrients accumulated over years of ocean feeding, decompose in the stream and forest environment around them. The nitrogen and carbon in a salmon carcass are chemically traceable back to the plankton in the open Pacific. Bears carry salmon carcasses into the forest interior, leaving marine nutrients in places miles from the stream. Ravens and eagles scatter pieces of fish even further. Insects consume the remains and are eaten by songbirds. The trees along salmon streams grow measurably taller and faster than trees along streams without salmon runs, because they are fertilized by the ocean, delivered by a fish. The salmon is a biological pipeline between two completely different ecosystems. It is the mechanism by which the Pacific Ocean invests its productivity into the interior of entire continents. No other animal performs this function at the same scale in the Pacific, and no other animal's collapse would have such widespread consequences across both marine and terrestrial environments simultaneously. If salmon are royalty, they are a king that rules two kingdoms at once. But we have not yet considered the reef. And the reef is a contender that changes everything about this conversation. Coral reefs are often described as the rainforests of the sea, an analogy that captures their biodiversity but understates their structural role. A rainforest is built by trees. A coral reef is built by animals. The coral polyp is one of the smallest and most underestimated rulers in the Pacific. An animal so tiny that you need a magnifying glass to see its individual details. Yet together, these animals have built structures that are visible from space. The Great Barrier Reef, which sits at the edge of the Pacific, stretches for over 1,400 miles and represents over 25 million years of continuous biological construction. The coral reefs of the Indo-Pacific, the most biogeographically diverse region in the world's oceans, support more species per unit area than any other marine habitat on Earth. Reefs occupy less than 1% of the ocean floor, yet they are home to an estimated 25% of all marine species. They are the most concentrated expression of biodiversity that the ocean has ever produced. The coral polyp builds this empire using a partnership. Inside its tissue, single-celled algae called zooxanthellae perform photosynthesis, converting sunlight into sugars that feed the polyp and allow it to deposit calcium carbonate and grow its skeleton. The algae receive shelter and the minerals they need. The polyp receives energy it could not produce on its own. This is one of the most successful partnerships in the history of life on Earth, and it has been running for over 200 million years. A healthy reef is not just a habitat, it is a food factory. The productivity of reef ecosystems supports fishing communities across the Indo-Pacific and the Pacific Islands. An estimated 1 billion people depend partly or wholly on reef-associated fisheries for their food security. The reef's productivity radiates outward into the surrounding ocean through the movement of fish, the drift of larvae, and the export of organic matter. Reefs in good condition can feed the open ocean as much as the open ocean feeds the reef. Reefs also protect the land. Coral structures dissipate the energy of incoming waves more effectively than any engineered breakwater. They protect coastlines from storm surge, erosion, and the grinding power of swell that would otherwise devour beaches and damage infrastructure. Pacific Island communities have lived in the shelter of reefs for thousands of years, and the structural protection those reefs provide is now measurable in economic terms. Replace a reef's wave-damping function with engineered alternatives, and the cost runs into the hundreds of billions of dollars globally. So the coral polyp, individually smaller than a grain of rice, has built the most biodiverse habitat on the planet, supports 1 billion people's food supply, protects thousands of miles of coastline, and maintains a biological productivity that radiates through the surrounding ocean. Is that supremacy? It comes close, but the reef cannot exist without the ocean conditions that sustain it. It is supreme within its environment, but it cannot create its environment. Something else does that. Now we need to go somewhere few visitors ever reach. We need to go down. The open ocean, the vast mid-water zone between the sunlit surface and the lightless deep, is often treated as empty space between more interesting places. It is not empty. It is the largest habitat on Earth by volume, and it is full of life operating on different rules. The creatures of the midwater zone, the mesopelagic and bathypelagic layers, have evolved to exist in a world of permanent twilight or complete darkness. Under pressure that increases with every meter of depth, in water so cold that biochemical reactions must be specially configured to function. The giant squid is the apex predator of the deep midwater Pacific and one of the most mysterious large animals on Earth. It can grow to more than 13 meters in length, making it one of the largest invertebrates ever documented. Its eyes are the largest of any living animal, reaching 30 centimeters in diameter, evolutionary adaptations for gathering light in the near darkness of the deep ocean. Its arms are lined with suckers, each ringed with sharp, tooth-like serrations that grip prey with extraordinary force. The giant squid is hunted by the sperm whale, and the relationship between these two animals is one of the most dramatic predator-prey interactions in the natural world. A sperm whale dives to depths exceeding 2,000 meters in complete darkness, navigating entirely by sonar, clicking at frequencies that bounce off prey and return as echoes read by an acoustic system of extraordinary sensitivity. The whale hunts the squid, The squid fights back. The scars of giant squid suckers are found on the skin of virtually every mature sperm whale in the Pacific, testament to battles that occur in the absolute darkness of the deep ocean and that no human has ever directly witnessed. The sperm whale is itself a contender for Pacific supremacy. It is the largest toothed predator on Earth. It has the largest brain of any animal ever known to have lived. It is one of the deepest diving mammals, regularly reaching depths where the pressure would crush a human body like paper. Its sonar is so powerful that some researchers believe it may be capable of stunning prey with directed sound bursts. It communicates in a complex series of clicks called codas, which vary between family groups in ways that suggest dialects, and which are passed down through generations in patterns that mirror the cultural transmission we see in orcas and humans. A sperm whale matriarchy, a group of related females and their young, occupies a specific region of the Pacific for decades, learning the currents, the prey distributions, and the seasonal patterns of their territory the way a skilled hunter learns a landscape. The knowledge accumulated by an experienced matriarch is of enormous practical value to every animal in her group, and her death represents a loss of navigational and ecological intelligence that the group cannot easily replace. The sperm whale is powerful enough and intelligent enough to compete for supremacy on almost any measure. And yet, like the orca above it, it depends on the health of the system below it. Its prey, the giant squid, depends on the midwater fish and crustaceans it consumes. Those midwater organisms depend on the organic matter that rains down from the sunlit surface above, and that organic matter is the dead and dying remnants of phytoplankton blooms, zooplankton carcasses, and the fecal pellets of every animal in the surface layer. The deep ocean is fed by the surface. The rulers of the deep are downstream of the rulers of the light. Let us now examine a ruler that operates not through predation or physical dominance, but through sheer biological leverage. The sea otter was hunted to near extinction in the Pacific during the 18th and 19th centuries, reduced from a population of hundreds of thousands to fewer than 2,000 individuals. When its numbers collapsed, the ecological consequences were so dramatic and so immediate that they gave scientists one of the clearest demonstrations of what ecologists call a Keystone species effect, the disproportionate influence that a single species can exert over an entire ecosystem. Without sea otters, sea urchin populations in the nearshore Pacific exploded unchecked. Sea urchins eat kelp. With no predator to control them, urchin populations consumed entire kelp forests, reducing dense, multi-layered ecosystems of extraordinary biodiversity to bare rock covered in nothing but urchins. These urchin barrens, as they are called, are nearly devoid of life. The fish that lived in the kelp disappear. The seals and sea lions that hunted those fish relocate. The seabirds that fed in the kelp canopy abandon the area. An entire ecological community built over centuries dissolves in a matter of years because one small mammal is missing. When sea otter populations begin to recover, the effect reverses with equal drama. Urchin numbers fall. Kelp regrows, fish return, seals return. The system rebuilds itself from the point of the Keystone species outward. The sea otter doesn't produce food. It doesn't cycle nutrients. It doesn't span multiple ecosystems the way salmon do, or fertilize the ocean the way whales do. It simply controls a single relationship in the food chain, the relationship between urchins and kelp, and that single relationship holds up an entire coastal ecosystem. That is keystone power. The ability to determine whether a system exists at all. The Pacific is full of keystone relationships. Remove the sharks from a Pacific reef system and the mid-level predators they normally control. Species like rays and grouper proliferate and consume the herbivorous fish that graze algae from the coral surface. Without those grazers, algae overgrows the coral, blocking light and eventually smothering it. A reef that was thriving becomes an algae-dominated rubble field, and the transition can happen in under a decade. The shark was not the most numerous species on the reef. It was not even the most visible. But its presence organized the relationships between every other species in the system, and its absence allowed the whole structure to collapse. This is why the question of supremacy in the Pacific cannot be answered by size or speed or aggression alone. The ocean is not a hierarchy with one dominant species controlling all others. It is a web with critical nodes at every level. Remove a node anywhere in the web, and the structure shifts, sometimes catastrophically. True supremacy is not about being the strongest. It is about being the most essential, the species whose presence or absence determines the fate of the largest number of other species. By that measure, the contest narrows. The orca is supreme in its ecological role as intelligent apex predator, shaping the behavior of every species it hunts across enormous stretches of open water. Its influence is real and measurable, from the distribution of grey whale calves to the foraging behavior of sea lions to the abundance of salmon in rivers, hundreds of miles from the nearest orca sighting. The blue whale is supreme in its role as nutrient pump, moving the chemical building blocks of ocean productivity from deep water to the surface and back, acting as a living circulation system for the chemistry that makes all ocean life possible at scale. The salmon is supreme as an ecosystem bridge, carrying marine energy into terrestrial environments and connecting the open Pacific to the forests and rivers of 3 continents. The shark is supreme as a behavioral regulator, not through the kills it makes, but through the fear it generates, reshaping the behavior of species across entire reef and coastal systems simply by being present. The coral polyp is supreme as an architect, building the most biodiverse habitat in the ocean, and providing the physical structure on which thousands of other species depend for every aspect of their lives. The sea otter is supreme as a keystone, holding entire coastal ecosystems together through a single critical predatory relationship that cascades upward and outward into every corner of the nearshore Pacific. But none of these, not the orca, not the blue whale, not the salmon, not the shark, not the coral, not the sea otter, can make its claim without the foundation. Phytoplankton are the answer. not because they are the most dramatic, not because they inspire awe the way a breaching whale does, or fear the way a great white does, but because they are the source. Every calorie in the Pacific food chain begins with photosynthesis performed by a single-celled organism drifting in the sunlit surface layer. Every apex predator, every keystone species, every architect of biological structure in this ocean owes its existence to the energy that phytoplankton capture from sunlight every second of every day. The orca's intelligence is real and extraordinary, but an orca without food is simply a very intelligent corpse. The blue whale's size is record-breaking and awe-inspiring, but a blue whale in an ocean without krill is a magnificent creature with no future. The salmon's ecological function is irreplaceable, but salmon without phytoplankton-based food chains have nothing to eat in the open Pacific and nothing to accumulate before they return to their rivers. The shark's control over reef ecosystems depends on a reef full of prey, and that prey depends on the zooplankton and algae that phytoplankton sustain. The coral polyp is an architect, but it builds with living chemistry, and that chemistry is driven by the same photosynthetic processes that phytoplankton perform out in the open water. Phytoplankton produce approximately half the oxygen in the atmosphere. They fix billions of tons of carbon every year, making them one of the primary regulators of the planet's carbon cycle. They are the foundation of the food web, not just in the Pacific, but in every ocean on Earth. They have been doing this for over 2.5 billion years, longer than any animal has existed, longer than complex multicellular life has existed. They have survived every extinction event in Earth's history. They were here before the sharks. They were here before the coral. They were here before the whales. And if every other species in the Pacific disappeared tomorrow, phytoplankton would continue. They would rebuild the food chain from scratch, as they have done before. That is what supreme means. But the story of Pacific supremacy does not end there, because the question of which species reigns supreme takes on a different character when we ask it in the context of the present rather than the past. The Pacific of today is not the Pacific of 100 years ago. The hierarchy of influence has been disrupted. A new force has entered the system, one that has no natural predator, no evolutionary checks, no biological limit on the pressure it can apply. And that force is changing the answer to our central question. Human activity now shapes the Pacific at a scale that rivals the natural forces of wind and current. Industrial fishing removes tens of millions of tons of marine life from the Pacific every year, specifically targeting the mid and upper levels of the food chain, where energy is most concentrated and most commercially valuable. When large predators are removed faster than they can reproduce, the species they preyed upon grow unchecked. When schooling fish like anchovies and sardines are harvested at industrial scale, the whales and seabirds and larger fish that depend on them face food shortages that play out across entire ocean basins. Plastic pollution has reached every corner of the Pacific. The Great Pacific Garbage Patch, a diffuse accumulation of floating plastic debris driven by the North Pacific Gyre, contains an estimated 80,000 metric tons of plastic, with concentrations up to 20 times higher than the surrounding water. Microplastics have been found in the gut contents of fish, seabirds, marine mammals, and invertebrates at every depth of the Pacific, from the surface to the Hadal zone at the bottom of the Mariana Trench. Animals that consume plastic do not extract nutrition from it. They may feel artificially full while actually starving. The plastic physically occupies space in their digestive systems that should be filled with food. Ocean warming is shifting the distribution and timing of every biological process in the Pacific. Phytoplankton blooms, which depend on specific temperature windows and nutrient upwelling patterns, are occurring earlier, later, or in different locations than they have for thousands of years. Krill populations, which depend on cold water, are moving poleward. The salmon that evolved to feed on those krill are following their prey, but the rivers that were born to return to have not moved. The mismatch between where food is and where spawning habitat is creates mortality across the entire salmon system. Coral bleaching events have become more frequent and more severe as ocean temperatures rise. A bleaching event occurs when ocean temperatures exceed the thermal tolerance of the symbiotic algae inside coral tissue. The stressed polyp expels the algae, losing its primary energy source and turning white, hence the term bleaching. If temperatures return to normal quickly, the algae can return and the coral can recover. But if temperatures stay elevated for weeks, the coral dies. Large-scale bleaching events that once occurred once per decade are now occurring every few years across the Pacific, and the reefs are not recovering between events fast enough to maintain their structure and diversity. Ocean acidification, the result of the ocean absorbing excess carbon dioxide from the atmosphere, is changing the chemistry of Pacific seawater in ways that directly threaten shell-building organisms. Pteropods, tiny swimming snails that are a critical food source for salmon and whales across the northern Pacific, have been found with shells that are visibly dissolving at the sea surface. Sea urchin larvae, which form the next generation of the animals that both damage and help maintain reef systems, are developing abnormally in acidified water. The acid eats away at the biological infrastructure of the food chain from the bottom, threatening the very organisms that the entire system is built on. And here is the uncomfortable truth that emerges when you put all of this together. The species that has the most power to determine which other species reign supreme in the Pacific right now is not the orca. It is not the phytoplankton. It is not the shark or the whale or the salmon or the coral. It is us. Human beings now exercise more influence over the Pacific Ocean than any other single species. We determine how many fish are removed from the system each year. We determine how much carbon dioxide enters the atmosphere, and therefore how much the ocean warms and acidifies. We determine whether phytoplankton blooms remain on their historical timing or are pushed into new patterns that the rest of the food chain cannot keep up with. We determine whether reefs receive the protection they need to recover between bleaching events, or are additionally stressed by runoff and fishing pressure that leaves them too weakened to bounce back. We determine whether orcas have enough salmon to feed their pods or face the slow starvation that has been documented in resident orca populations where salmon stocks have collapsed. This is not a comfortable position to occupy. To be the most influential species in the Pacific Ocean is not a title that comes with pride. It comes with the weight of consequence. Every decision made about energy production, about fishing regulation, about land use, about plastic production, ripples into the Pacific and determines which of the ocean's natural rulers gets to keep ruling and which begins to decline. But influence in both directions. If human activity can degrade the Pacific faster than it can recover, human choices can also allow the Pacific to recover faster than it would degrade. Marine protected areas, when properly enforced and carefully designed, allow fish populations to rebuild. Kelp forests that have been converted to urchin barrens can recover in years when otter populations are restored and urchin harvesting is managed. Whale populations that were reduced to fractions of their historical numbers by commercial whaling have grown substantially since the moratorium took effect. Sea turtle populations on monitored nesting beaches have increased where egg harvesting has been stopped and nesting habitat protected. The Pacific is resilient. It has been rebuilt before. After the mass extinction 66 million years ago that ended the age of the dinosaurs, the ocean's food webs collapsed almost entirely. Within a few million years, they had rebuilt from the survivors. Within tens of millions of years, the ocean was as diverse and productive as it had been before. The Pacific does not need us to save it in any cosmic sense. It will persist. What is at stake is the version of the Pacific that exists within any human timeframe, the version with blue whales and orcas and coral reefs and salmon rivers and albatrosses crossing thousands of miles of open water on wings built for the wind. That version of the Pacific requires us to make different choices than we are currently making. Not dramatic, heroic choices that require abandoning modern civilization, but incremental, sustained choices that reduce the pressure we apply to a system that is still willing to respond. Fish with selectivity rather than with maximum efficiency. Reduce the carbon load we are adding to the atmosphere at a pace that gives biological adaptation a chance to keep up. Protect the coastal and offshore areas where the most sensitive and most productive communities of life exist. Reduce the plastic we produce and improve the systems that keep it out of ocean currents. And perhaps most importantly, maintain our attention. The Pacific is easy to ignore. It is vast, remote, and mostly invisible to the people living far from its shores. The battles for supremacy that we have traced in this film, between orca pods and grey whales, between phytoplankton and the zooplankton that feed on them, between the coral polyp and the warming water that threatens to destroy it, happen out of sight of most of the world. They are real, they are ongoing, and they matter enormously, but they require us to look. So who truly reigns supreme in Earth's largest ocean? The honest answer is this: the Pacific has no single sovereign. It has a hierarchy of influence that shifts with depth, with geography, with season, and with scale. The phytoplankton reign at the base of all productivity, and nothing that lives in the Pacific escapes that foundational authority. The orca reigns at the apex of intelligence and behavioral complexity, and its influence shapes the ocean from the top down in ways no other predator matches. The coral polyp reigns as the greatest architect of biological structure, having built the most diverse habitat in the ocean over millions of years of patient construction. The salmon reigns as the greatest connector, linking the open Pacific to the hearts of continents. The shark reigns as the oldest ruler, 400 million years of unbroken dominance encoded in a body that barely needs to change. Each of these rulers is supreme within its domain. Each is essential to the function of the whole, and each is, in its own way, dependent on every other. The Pacific is not a kingdom with one ruler. It is a republic of interdependence, with power distributed across every level of the food chain and every corner of the ocean, held in balance by relationships so intricate and so ancient that we are still discovering their depth. Understanding that is the beginning of wisdom about the Pacific, not the naming of a single king, but the recognition of a system so complex and so interconnected that the question of individual supremacy dissolves into a larger truth. Every species matters. Every relationship matters. Every node in the web, from the phytoplankton to the orca, from the coral polyp to the sperm whale, from the sea otter to the salmon, holds a piece of the structure together. Remove any one of them, and the structure shifts. Remove enough of them, and it collapses. And then there is no king and no ocean left to reign over. The Pacific is still here. Its rulers are still ruling, diminished in some cases, resilient in others, but present. The blue whale still sings across hundreds of miles of open water. The orca pod still coordinates hunts that no individual animal could perform alone. The phytoplankton still bloom in their billions every spring across the nutrient-rich zones of the North Pacific. The salmon still run in rivers that still flow toward beaches where the next generation is already waiting in the gravel. This is Unknown Genesis 4K. The Pacific is still speaking. Its